Thanks. Hi, everyone. I'm Rachel Bowens Rubin. I'm a final year PhD student at UC Santa Cruz. And my research is in both conducting high contrast imaging observations and developing adaptive optics instrumentation for adaptive secondary mirrors. And today, I'm really excited to be sharing with you some of my observing work. This is work that corresponds to a paper that was released on arXiv today. And will soon be published in AJ and it's about a joint radial velocity and high contrast imaging survey that I led of one of the nearest systems, Wolf 359. And I want to do a special shout out to, there's a whole bunch of people who are co-authors on this paper in this room. Joey Murphy especially, I want to give a shout out to, who did a lot of the RV analysis because I am not an RV person. Maybe I'm an RV person now, but yeah, big special thanks to everyone who has been helping me with this. Okay, so now we can begin our tale. A short time ago, in a star system very, very close, there was born an M dwarf, Wolf 359. Wolf 359 is an active M6 star, weighing in at about 1/10 of a solar mass. It's the 5th closest system to us at 2.4 parsecs, and it's so close, in fact, that the NASA New Horizons team chose this star to demonstrate how its parallax changed as New Horizons moved away from the Earth. It's a relatively young system. In this paper, we place the age between about 100 million years and 1.5 gig years. And the combination of this system's youth and its proximity to Earth makes Wolf 359 an ideal system for searching for companions using direct imaging in the infrared. The proximity makes any potential companions appear at proportionally wider separation angles from their host star from our vantage point, and it boosts the apparent magnitude of a companion logarithmically. And this becomes just an incredible advantage for what we can do with the when we're doing direct imaging within the 5 parsec sample, like with Wolf 359. And Wolf 359's proximity also makes its star system of high public interest, and it's popular in many sci-fi stories. One of the most popular inclusions of Wolf 359 is in the Star Trek franchise and the famous Wolf 359 Battle of the Borg. I can't go without mentioning this today. September 8th happens to be Star Trek Day. That was a definitely perfectly timed arXiv release that I definitely intended. Anyway, so happy Star Trek Day, everyone, and I bring you my personal battle with Wolf 359. In 2019, Mikko Toomey and his team released a preprint paper containing an RV data on hundreds of M dwarfs, including Wolf 359, and they identified a long period RV candidate that could point to a cold Neptune-like exoplanet with an approximately 8-year orbit, which is now Wolf 359b. And when I was a naive first-year grad student, I was browsing a list of nearby exoplanets when I noticed Wolf 359b. And it looked like it had some properties that can make it an interesting direct imaging target, like youth, wide orbit separation. So I asked my advisor, Phil, why the system had not been directly imaged, and he wasn't completely sure, and so I went on a quest to try to answer it. And we used information from the RV data set to predict companion separation and brightness to understand if this would make a good candidate for imaging. When we tried to predict the separation of the Wolf 359b candidate on a given night, we found that there was a lot of uncertainty. Again, this was an RV candidate planet. We knew that we would likely be outside of the NERC2 diffraction limit, but given the uncertainty, we weren't completely sure when the planet would be at its max separation. And so we thought it would be best to do this observation using the vortex coronagraph in case we didn't catch the planet at the widest part of its orbit. And we elected to use the L and M band vortex, mostly for not knowing the separation well. And then I predicted the mass from the measured M sin I, and then applied the Linder low mass cooling curves with the age estimates to make a brightness estimate. And I'm pointing this out to this community. When I was originally evaluating how much telescope time we would need, I used the Keck Observatory's NERC2 SNR and efficiency calculator. And we found that with like 3 to 4 half nights of data collection using the M filter, we would have about a 50% chance of making a 5 sigma detection on Wolf 359b. and a 2/3 chance of making a 3 sigma detection. Sounded pretty good. This is assuming we caught the planet at sufficient separation from the star. And we found sort of that it was on the cusp of detectability specifically at 4.6 microns, which is as infrared as NERC2 can go in the M band. And using L band was just completely infeasible based on the models because of how cold Wolf 359 was predicted to be. So there would only be a reasonable flux at a wavelength longer than 4 microns. So M band was our only hope. I think my advisor was a bit shocked when I returned with the answer that this imaging observation could be possible. It was high risk, but it was high reward. It was a situation that would depend on us getting a bit lucky about the youthfulness of the system and the mass space of Wolf 359b. But if we succeeded, it could be the first Neptune-like exoplanet measured with a direct imaging detection. And in the scenario that we didn't find a companion, our imaging survey could still put upper limits for the companion down to sub-Jupiter masses. Keck had also just finished an infrared pyramid wavefront sensor upgrade, which is ideally suited for performing adaptive optics corrections when using M dwarfs as a natural guide star. The IR pyramid uses H band rather than R, like the Keck-Hartman. And Wolf 359 is about 5 magnitudes brighter in H than R. And so our survey could really take advantage of this unique new capability in the adaptive optics system. Our issues in trying to determine what would be the best time to conduct this observation really brought in this need for improved RV analysis very early and like right at the forefront of our planning. And we wanted to know, were we just crying a wolf planet, or was there an actual wolf planet? And so we started a partnership with the radial velocity community to try to address this candidacy issue. And we applied for Keck HiRIS time in collaboration with the California Planet Search team. Thank you, Andrew and Howard, who are here. And we wanted to extend the original 20-year baseline for Wolf 359. We were able to get 12 additional HiRIS points in a region of phase space that was sparsely covered in the orbit of Wolf 359b, extending the data set with the longest baseline. HiRIS was the longest baseline before this. We were also able to work with Ignacy Ribas from the Carmenes team, who gave us access to the Carmenes 3-year GTO data early. And we also partnered with Jacob Bean and the Maroon X team, who were the most generous, and we added 68 of their measurements that had not been previously published to the RV baseline. Maroon X also provided Chicago-style pizza for one of our observing nights, and we've been really grateful and encouraged by the openness of the RV community to collaborate with us. And then I'll give a spoiler here. Spoiler here on the RV results, we more than doubled the number of RV points in the original analysis, but we are not able to prove or disprove the Wolf 359b candidate with our new RV data set. We very clearly detected the rotation period of the star, which is 2.7 days. And you can see the rotation period fit in blue. It looks like a big blue block on the left of the RV time series plot. And the corresponding RV completeness plot for what we could detect is on the right. We find that we have about a 30% completeness to the Wolf 359b candidate as reported by Tuomi, which is not enough to definitively say yes or no to it. Okay, so our only hope is NERC2 imaging now. And we pick up our story again back in 2020 A observing semester. The TAC had just granted us time across 4 half nights to conduct our deep NERC2 survey. But unfortunately, our first 2 nights were canceled because of a poorly timed ice storm. And then our second 2 canceled because of a poorly timed pandemic. But in 2021, we came back strong. We ended up collecting about 5 hours of total integration time over 600 images. Okay, so the data are in. What did we find? Blank sky. We didn't detect the companion. We didn't even see anything to 1 sigma detection. At least there were no Borg cubes. However, our contrast curves were more background limited than we originally predicted. and we were not able to probe the smallest mass spaces that we hoped. We seem to hit a limit of about 14 and a half mags or so in the background regime for each half night, but I'm going to get back to that. First, let's go through just what our data can tell us. Here's our 5 sigma contrast curves for each individual night, and then the combined data set nights. But let's remember how close Wolf 359 is, and change this from to absolute mag and orbit separation listed in AU. And here's our combined contrast curves for 1, 3, and 5 sigma, written in AU for the system. And yes, that x-axis is 0 to 4 AU, and that's a lot tighter than we imaging folks are typically used to thinking about. But let me put where we think the Wolf 359b candidate was on the graph at 1.8 AU. Check it out. We have great sensitivity to that, and that's really cool to see. Just thinking about what mass range that corresponds to, we used the Ames, Cond, and Linder-Lomas models to convert our contrast curves from magnitudes to planet brightness, and this is what we get for a spread of ages for Wolf 359 going from 100 million years to 1 gigayear. We then converted these mass contrast curves to survey completeness, sort of like what I was showing for the RV plot. We use the ExoDMC package to make this. And so let's just zoom in on our completeness plot for a second. We're getting really good coverage in that 1 to AU semi-major axis region where we thought the candidate was, but we're not getting the mass coverage that we really want to be able to say anything about this. And so I mentioned at the beginning that we predicted that we could cover this space, but why? So why didn't we get the sensitivity we expected, and how big was that gap? Really big is the answer. I'll try to go through this sort of quickly since I'm out of time, but this performance gap was 1.7 mags. And we know that part of this discrepancy from the NERC2 calculator was because we can't, with the NERC2 calculator, put in that we're using the vortex, and the vortex coronagraph has some throughput hit associated with it. And you can look in my paper, and I show that there is about a 60% throughput hit just by using the vortex coronagraph and M-band. So that's really big. Doing that adjustment, we still don't account for the full performance gap. We have a suspicion that there is an issue with correction of the background and due to water vapor changing in the atmosphere. And if our suspicion is correct, it's very possible that the new commissioned NERC2 electronics will help us correct the background better and start to close this performance gap as well. I'll say I'm on the job market, and I'll wrap up there, and I'll leave my summary slide up and open the floor for questions.